to the concepts video on sinusoidal graphs. So let me start off by defining a different definition, not of sinusoidal graphs, but of periodic functions. Okay, so what is a periodic function? So we know what a period is. It's just like kind of like a chunk of time over which something happens. So this is a periodic function is a function for which a specific horizontal shift, and I'll abbreviate, horizontal shift, so basically you shift your graph, results in the original function that you started with. Original function. Okay, so what does this mean? Well, pictorially, let's say we have something like this. Let's say we have our x squared graph, right? So our normal parabola. Okay, so this is our x squared graph. If we shift it, let's say, I don't know, this many units to the right, so now let's say it's over here, this doesn't look like the original function, right? I mean, it looks similar to it, but it doesn't look exactly like it. Like, we can obviously tell that it was shifted over by that much, right? So this x squared graph is not a periodic function, okay? So the formula for a periodic function would be the following. It would satisfy, so if we had a periodic function, like this guy here, okay, let's say this one is periodic, and we'll go into more detail on what periodic functions actually look like. But anyways, let's say some function is periodic, right? So then, what our definition says is this is a function for which a specific horizontal shift, so that means you add something or subtract something from your x value, right? For each of your input values, this results in your original function. So this should equal f of x for some given p, and this is a constant. Okay, so this is a constant that represents your horizontal shifting, alrighty? And this is defined, the p here represents our period, okay? Hence the name periodic function. So this is the period, which is the given, or a specific, I'll just call it the specific horizontal shift by which this is true. Okay, so the specific horizontal shift, this is a constant for any given periodic function. Okay, it doesn't change. Alrighty, so now let's get into more of the details on, like, okay, so how do we find what a periodic function is and what do they even look like? So the first thing is that if we write this formula again, okay, so we have some function for which you can shift it by a certain amount p, and it looks exactly the same as it did before. Okay. So what this means is that we're going to have some kind of repeating pattern. So we have a repeating pattern, okay, of function or output values. All right. Okay, so what does this mean now? This is really confusing. But let's take a look at the unit circle actually. Okay, so let's say we have our circle, right, and here are our quadrants. And let's see if we can find any such pattern for which you put in a certain input and then you get out a certain output, and then some pattern kind of repeats over and over. So let's say we look at sine, okay? So let's say we're looking at sine of theta, and theta, let's say it's just your angle, right, measured from the horizontal x-axis, okay? So sine theta, let's say we look at that. Let's look at a chart of what our values look like. So as theta changes, how is sine theta changing? Okay, so let's say theta is equal to 0, okay? So theta is equal to 0, so we're on the x-axis, and our sine, which is like our y value, kind of like our y value, right? That's also 0. Okay, so we start there, that's good. Let's see, how about, let's say we do pi over 6. Okay, so now we're around here, and our sine should be 1/2. Okay, then we go to pi over 4, we're going around the circle here. Pi over 4, we get a y value, or a sine value, of radical 2 over 2. Okay, then we move to pi over 3, or 2 pi over 6, right? So then we get radical 3 over 2, and let's say we go all the way 90 degrees, or pi over 2, then we're going to get this positive 1, okay? And we're going to keep going around, and basically, if we were to plot these values, this is our input, theta, our angle is our input, and sine theta is our output, we would get something that looks like this. Okay, so let's say this is our theta axis, right, our input, and this is our sine of theta axis. Okay, here's 0. Let me label this up to pi over 2, and then here's pi. So here's pi over 2, here's pi. So this is what we would get. and here's, let's say, positive 1, okay, and here's negative 1. So 0, 0 is the point right here. Pi over 4 would be here. Okay, so pi over 6 is somewhere in there. Pi over 3 is somewhere in there as well. Basically, so at pi over 4, we're at radical 2 over 2, okay, and then at pi over 4, we're at radical 2 over 2, right? So that's somewhere around here, kind of. And then at pi over 2, we hit 1, right? So we go all the way up to 1. And then if we were to continue along, so we ended at pi over 2, let's say we do 2 pi over 3, right? So 2 pi over 3 is here. Then we can see that our y value starts to drop, right? Because our y value never goes above 1, okay? So if we were to plug in, here's another point, 2 pi over 3, I did that backwards, 2 pi over 3, that theta value corresponds to a sine value of exactly radical 3 over 2. Okay, so then we start kind of heading down as we pass pi over 2, right? So we're going to get actually a curve that looks something like this. And then we see that when our theta equals pi, our sine is equal to 0 again. So we should reach back to 0 here. Okay, and then we see that as we travel along the unit circle, our sign becomes negative, right? But it has the same kind of shape. So it's actually just going to flip below the axis. And let me continue this on the next slide so we can see what the full sine graph looks like. All right, so we have something like this. Here's our theta, and here's our sine theta. Okay, here's 0. Let's say this is pi over 2, pi, 3 pi over 2, and 2 pi. Okay, so this is what I had drawn before. So this is positive 1, this is negative 1, right? So at pi over 2, we're at 1. At pi, we're at 0, because sine equals 0 when our angle is pi. At 3 pi over 2, so if we look at it, here's our unit circle again. Here's 3 pi over 2. Then our sine value, our y value, is equal to negative 1. So that's going to be right down here. And when we get back to 2 pi, our sine goes to 0 again. Okay? So we have a curve that looks kind of like an S, sort of like sideways S-shaped thing. Okay, it goes up, it starts at 0, goes up, maximum of 1, goes through 0 again at pi, goes to a minimum of negative 1, and then goes back to 2 pi. Okay, now, so this is what's called one cycle, okay, because we went around the unit circle one time. And not only that, this is just specific to the unit circle, but one cycle corresponds to one segment of your graph, or of your function, okay, that is the repeating, or we could say, repeating pattern. Okay, so for our example, for our sine graph here, we can see that, let's say, okay, so we started at 0, theta equals 0, we went around all the way to 2 pi, right? Let's say we were to continue going around, so follow it around again, we're going to see that the same output values, or the same sine values, are repeated, right? So let's say we extend this graph, okay, here's 3 pi, okay, and here's 4 pi. We're going to the next one over here. But anyways, so it's basically going to start at 0, go up again, go down, and go up. And it'll be the same for the left side too. Let's say we go this way to negative pi or something. Then we're going to see it go like this and drop below the x-axis and go along. So what we were studying first was this segment here, right? We went from 0 to 2 pi. And then we see that pattern, this one cycle, right? This repeats because we can see it copied exactly right next to it, right? Okay, so we see another one here, and if we went to the left, we'd see that same exact pattern, okay? So that's why sine, a sine graph, or sine of theta, is a periodic function, because we can identify a horizontal shift for which our graph repeats itself, okay? So what is our horizontal shift in this case? That would be like saying, okay, let's look at this one cycle that we have here, right? We're going to look at this middle one that we started with. Let's pick a point on our graph, just something easy. So let's say we pick pi over 2 and positive 1. That's a point, right? So we have pi over 2, comma, positive 1. Okay, so now what we need to do is find out how much of a distance is there in between, or like what is the difference between this input value, the pi over 2, and the next input value, which gives us that same point on the repeated pattern. So that would be right here, right? Because we can see, okay, this is the top of the peak again, and this value happens to be a 5 pi over 2, right? Because that's 2 pi plus pi over 2, okay? So what does this tell you? The difference in the horizontal, or the input values that give you out the same output value, or the same place on your repeating pattern, the difference between those, so in our case this would be 5 pi over 2 minus pi over 2, so this difference, which gives us 4 pi over 2, which can be reduced to 2 pi, this thing here, this is the constant horizontal shift, right, that we were talking about in the very beginning, and this is called our period. Okay, and you could do this not only with these 2 points, but let's say you picked, I don't know, pi here, and so this is the point pi 0, right? And then you pick the next point to see how far that is from the copied value in the next pattern, in the next time the pattern repeats, right? And it's important to note that even though this point here, I know the picture's getting a little bit messy, but anyway, so this is the point pi 0, right? And so you wouldn't just look for any other point that has a y value of 0, because we could pick this point here, but we can see for sure if we look at these as like in their frames, right? That is definitely not in the same place as pi 0 is in its frame, because pi 0 is exactly in the middle, right? So when we look over to the next frame, we would look for the point exactly in the middle, okay? So that would be 3 pi, okay? So then you can also get our period from taking 3 pi minus pi, and we'll just get simply 2 pi. Okay, so we can see that period for a periodic function is constant for that function.